Computer Architecture. First, I like to introduce myself. I'm Novita and I will host you for today's event. Now, let me welcome our special guest for today. Welcome to the Honorable Dr. Joseph Teguh Santoso, as a Rector of STEKOM University, Indonesia. To the Honorable Professor Dr. Sugandhi Malhotra, as a Head Professor, Computer Science and Engineering. And to the next speaker, welcome to the Honorable Miss Letus Senzani, as lecturer in computer in the Department of Mathematics, and to the Honorable Dr. Sivakami, as an assistant professor, Department of Information Technology, and to the Honorable Miss Cherlina Helena Purnamasari Panjaitan, as lecturer Information Engineering Department, and last but not least, also to the honorable guests and audience today. Okay, before we begin, I have a few housekeeping notes here. Today's session is being live streamed on the Universitas STEKOM YouTube channel. And for today's event, we will start with Indonesia national anthems. In the next session, we will begin the main event presentation by our special guest for today and continue with the Q&A section. Take a picture for documentation and last time is closing. Okay, first we will sing our national anthems for the Mr. Abdullah. You can start the session today. Thank you. Okay, thank you. And we will continue to the main event. For our audience, if you have any question for the speaker, please add them to the chat or you can raise your hand. We'll be able to answer some of the during the Q&A session after the presentation. And today, its presenter will have about around 30 minutes for the time presentation. Now, let's please welcome our first presenter, Professor Dr. Sugandhi Malhotra. The time is yours. Thank you.
Yeah, thank you, Novita. Yeah, thanks a lot. So, yeah, good afternoon, everyone. So give me like a moment to share my screen. I hope that my screen is visible to you guys.
Yes, ma'am.
Yes,
Thank you, Novita. So the topic of the day is fundamentals of computer architecture, right? So Professor Sugandhi Malhotra, head CSE Apex, CGC University, Mohali, India. So what we're gonna discuss in this webinar is introduction to computer architecture, various components of the computer system, computer architecture and how it functions, memory hierarchy, instruction cycle. We will talk about the instruction cycle in detail about all the phases and all. So different IO devices and how the buses are connected with the different components of the CPU. and few modern trends in the architecture, which are very important. So definitely at the end, I would like to answer the questions, if any. So let's proceed ahead. So what is actually a computer architecture? Before we begin with our any discussion and all, let's start with a very simple question. What is computer architecture? So when we are talking about the computer architecture, it is the design and structure and behavior of the computer system. Design, structure, and behavior of the system components that define how a computer works. Right? They're the different components of the computer, how they are organized together, how they are structured together. It refers to their design and how those components, after connecting together, how they work. So that means computer architecture includes hardware organization, and hardware is of no use if the no software is installed on it, right? So hardware organization along with the software interface through which we gotta communicate with that hardware interface, right? So another is the instruction set. To operate anything, to work with anything, there exists an architecture, instruction set architecture that we are going to discuss in this conversation. So computer architecture, if I talk about at a whole, it talks about the hardware organization, it talks about the software interface, and it talks about the instruction set and design and structure behavior of the computer system altogether, right? So now, if I discuss the levels of the computer architecture, so levels of the computer architecture are further divided into three major bifurcations, right? Each level defines a different view of a computer system and how it operates. There are the three levels. Each level defines a different view of a computer system and how it operates. At the top level, if I talk about, there is ISA, instruction set architecture, right? For which defines a set of instruction, how the processor can execute whatever the instruction, whatever we are asking the computer to do, or whatever we are asking the processor to do. Definitely, in other words, in detailed term, we are asking the processor to perform, how the processor can execute and serve as an interface between the hardware and the software. So we require instructions for that, right? Set of instructions, or all a set of instructions together, called a program. So it specifies how program communicates with the machine using the instructions, different data types, different addressing modes, and definitely registers also. So we will talk about the ISA, that is the instruction set architecture at the top level. If we talk about the second level is the micro architecture, right? Which micro architecture deals with the internal organization of the CPU, that describe how instruction set is actually implemented, how instructions are actually implemented. That is defined by the micro architecture. It includes definitely CPU is further divided into ALU, control unit, if we talk about, and registers are part of it. How the pipelining of the instruction set architecture is done, that pipelining, fetch, decode, execution, and write back. So definitely the cache memory in turn plays a very vital role in designing of the micro architecture. The second level explains the micro architecture of a computer system, computer architecture. So if we talk about at the lowest level is the design, which consists of the complete hardware system. So if we talk about the hardware system, how the hardware system is designed, how the buses are there, the wires are connected together, input output devices are there, different storage devices are there, how those are all connected together, interconnected together to work as a system. So these three levels for the conceptual pyramid of the computer architecture, starting from the low level, that is the physical level is the low level, hardware level, and building up to the interface used by the software application. So this is all about the levels of the computer architecture. Once again, instruction set, that is the ISA. Then we have the micro architecture, where we talk about the internal design of the computer architecture. Then we have the system design, that talks about the hardware, right? So basic computer components, in a very layman language: input, output, and in between the processing. Input, output, and in between the processing. We already, like, this is trained into our minds, that the data is processed by the CPU, and at the end we get the information. Data is an input which is processed by the CPU, and we get the output. So data is fed into the computer through the input devices. There exists the various input devices, mouse, keyboard is there, touch panel is there, like lots of input, or through the voice also we can give the command, right? Which we find nowadays very fascinating and easy also, voice commands and all that act as an input. And mic is the mic is used as an input device. So then we have the central processing unit, which works on the data which is given by the input devices. Central processing unit consists of, as I discussed before also, it consists of control unit, CU, ALU, and register. So a control unit is connected with the control unit. Keep in mind, control unit is connected with the input and output. Another major point to notice is CPU is connected with the primary memory and not with the secondary memory. There is no direct connection between the CPU and the secondary memory if we talk about auxiliary storage. There is no direct connection between the CPU and the auxiliary storage. It is connected via the main memory. So if any kind of processing happens, if the data is not available in the cache, then it checks in the main memory. If the data is not available in the main memory, then it checks for the auxiliary, then it checks for the auxiliary storage. From the auxiliary storage, the data is transferred to the main memory, and then it is transferred to the processor for the execution, right? So at the same time, it is like copied to the cache also, because cache, the main term we always refer for the cache is frequently used instruction or frequently used data lies in the cache. So as soon as we copy the data from the secondary to the main memory, simultaneously it is copied to the cache also. After this, whatever the processing is required, either through the ALU is required, or we just want to pass that, or any kind of storage also we want to perform, then the data is transferred to the, after processing, the data is like further, if we want to save back, we can save back also. If we want to display it, we can display it in the on the output screen. So ALU is the unit which is used for performing the arithmetic and logical calculations, arithmetic operation and logical operations. So control unit is act as a centralized component, which is mainly like act as a passing on information between the different devices. So that is actually the central point or the brain of the computer, we call it. So the control flow, definitely we'll talk about like there the data buses are there is the the address buses are there are the control buses, control signals are there. Control signals, just for a moment I'll say that interrupts are given to the computer, right? Those are a kind of control signals are there, or otherwise the register is full, stack overflow, some kind of these kind of instructions are there. So those are passed through the control flow instruction. So data flow in this is shown with the solid arrows. And if I talk about the control flow, so control flow is depicted in this diagram in the dotted lines. So data is processed by the CPU, and after that the information is there. Either we want to display it, or we want to show it on any screen, or we want to print it. So CPU once again is, to summarize, CPU is once again is divided into control unit, ALU, registers are there, which is like address register, program register, instruction register. Many we'll discuss further also. So we have a main memory and secondary storage, auxiliary storage. So main memory, there is no direct connection of the secondary memory with the CPU. It is connected via the main memory, right? So next is the instruction cycle. How actually the instructions are executed onto our system, right? Onto our computer or processed by the computer. We spoke about the ISA, instruction set architecture, which consists of different, for every computer, one Newman architecture is there. There are the different architectures for every processor. So there are the instruction cycle, how instruction actually is executed. Commonly, if I talk about before discussing this diagram, there is a fetching the instruction. Then we have a decoding. Every instruction has a meaning, what that instruction means, decoding that instruction, then executing that instruction. After the execution, there comes the, after executing the instruction, whether we want to store back the result or anything. So that is called write back, right? Fetch, decode, execute, and write back. So these are the 4 steps whenever an instruction is executed. So now a question comes, where the instruction is, how computer comes to know that which instruction it has to execute. So definitely a question comes in the mind that which instruction the computer will execute next. So there exists a register called PC register that is known as a program counter register, which tells you the address of the next instruction to be executed. So if you observe this diagram, the first one is instruction address calculation. Instruction address calculation, the first and the form, if you find it at the bottom left, this circle, bottom left corner, there is a circle, oval is there, instruction address calculation. An instruction is found through the program counter. Program counter tells you the address of the next instruction to be calculated, next instruction to be executed. The address of that instruction is calculated, and from that address instruction is fetched. From that address the instruction is fetched and stored onto instruction register, right? So might be, for example, let's consider an example that the instruction is add a comma b. Correct? Add a comma b. Add is an operation and a comma b are the operands, right? So add a comma b, add is the operation and a comma b is the operand. Correct? So that instruction is kept onto the instruction register we have. Then after that instruction decoding, with that instruction decoding, we have found that we have to find out a and b, those operands we have to find out, and after that we have to perform the addition of those. Correct? So then the next task is, after the instruction decoding has happened, we have find out, or the computer processor has found that this instruction calls for the addition process. After that a comma b, where those operand lies, right? Where those operands lies. So next process is fetching those operand. There may be, like in the instruction only direct operand values are given, maybe 5,6 also we can sometimes write the direct values we can give, or we can refer to the address also, like a comma b lies at somewhere, any location, we'll fetch the operands from there. After that, definitely operands are stored at a particular address location. From there we'll fetch the addresses. After calculating the addresses, we'll fetch the operands. And then what happens after decoding, after operand fetching, so we will perform the operation on the operands, on the data, right? So next step is the execution, that is called the data operation. So why there is multiple operands? If the multiple operands are involved, then definitely we need to fetch again and again. So there are the word is written multiple operands, a comma b, as I spoke about. So then we execute the process, execute the instruction, right? So next is what? Now we need to store the result also, right? Store the result also. So where we gonna store that result? Either in the data register, or we gotta, like, it depends upon the, once again, on the architecture. If the instruction is add a comma b, it may be like, according to the architecture, it's a 2 address instruction or 3 address instruction, depends. So a comma b will be interpreted as, or will be decoded as a equals to a plus b, most probably, right? Or the maybe there is, if it is a 0 address architecture or any other architecture, it depends on whether we are saving the result in the data register, or by default saved in the data register, or in the first operand value, right? So after fetching or after executing the instruction, the results are again the result of the instruction is saved onto the, like depending upon the architecture where it would be saved, whether the data register or at the place of the a value, or it is 3 address instruction where the, like, the third value is the result storage value, right? So after processing this, once again the program counter will update, and it will include the address of the next instruction to be executed. So it will definitely all flow together, right? This instruction cycle will continue for all the instructions written in the program, right? So the next thing we are going to explain is the memory hierarchy. So when we talk about the memory, so we will start with the smallest. The smallest is, as we spoke also, registers. Program counter is one of the register. Instruction register is the type of register. We have address register, we have data register, we have stack pointer register. So definitely we'll speak about, like, few of the general purpose registers also, and few special registers also in the architecture. Then after the registers, we have the cache. So cache is further divided into L1, L2, L3, and there may be more levels also. But I mean, mostly there are the two levels only, L1 cache and L2 cache are there. After that, there comes the RAM, random access memory, or we call it like primary memory. So after the primary memory, nowadays in our computer, we are using SSD also. So solid state drives. So then we have solid state drives. Those are also known as the flash based memory. So we have the hard disk also, right? Mechanical hard disks also, that is at the last level. So normally if I talk about like the processors and the laptops in India nowadays come with the 512 GB SSD, and maybe it has an extension of terabytes of hard disk also, right? So it depends also like what kind of memory you are like you're acquiring when you're buying a laptop and all. So now, once again, let's elaborate this memory hierarchy. First comes the register. Register is mostly in the size of, in the form of bits. So 8-bit is there, 16-bit is there, 32-bit is there, 64-bit registers are there. So program counters, special registers. Let's talk about first about the special registers. So first is the program counter register. Program counter stores the address of the next instruction to be calculated. Instruction register holds the instruction fetch from the address given by the program counter, and after fetching the instruction is stored in the instruction register. Data register holds the operand. Then we have a stack pointer that defines the top of the stack. So these are few special purpose register. Then we have the general purpose registers also, which are denoted by AL. For example, A to G, I have some general purpose registers. So lower order bits are denoted with the name, for example, the AL. So AL denotes the lower order bits of the register A. So AH denotes the higher order bits of the register A. So for example, if I talk about that, it's a 16-bit, A register is 16-bit. So lower order bits would be 0 to 7. And after that, 8 to 15 are the higher order bits, right? So that is about the register. So there comes the cache. So cache is the expensive memory, definitely the expensive memory, but it is quick because it stores the frequently accessed data or instruction, whatever the instructions or whatever the data you are again and again accessing. So that gets saved onto the cache. So we can access it again and again, right? So definitely level one, first the CPU looks for any instruction. As I told before also, CPU looks for any command we are giving. CPU first checks the data onto the cache. So if the data is available in the cache, then it fetches the data from the cache. If it is not available, then it goes to the primary memory. In the cache also, first it will check for the L1 level. L1, if it is not available in the L1, those are the designated areas in the memory. It will directly go there. Smaller in the size as it is expensive also. If in L1 it is not available, it will go to the L2 and so on, right? Then comes the physical memory. So RAM is there, random access memory is there. Definitely it is, as compared to cache, it is a bit cheaper, but definitely as compared to the hard disk or SSD, it's expensive. So it has an average capacity also there. The SD RAMs are there, dynamic RAMs are there. So that is all about RAM. Whenever a program comes for, whenever a program is executed, it comes for execution onto the primary memory only. Then we have a solid state memory because hard disks are a bit slow, right? Due to the mechanical reasons and all. Then before a few years, solid state drives were evolved. So those are the flash drives, definitely at a speed of light. We always talk about in terms of flash. So those are expensive than the like hard disk, but definitely has a speed faster than the hard disk, mechanical hard disk, hard drives, right? So this is all about memory hierarchy. So then comes the CPU buses. How all these components which we spoke about, CU is there, ALU is there, so motherboard is there. So different components of the system are all connected together. If you talk about like in terms of CPU memory input output, which makes our computer system, this is connected via the 3 buses, right? Control bus is there, address bus is there, data bus is there. Control bus is there, address bus is there, data bus is there. The arrows here, the connection of arrows with the CPU memory IO to all these buses is very important. Control buses carry the control signal. Address buses carries the address of the memory location, address of the register, or any address of any particular location. So database carries the operands, right? So control buses carry the control signals like interrupt is there, masking is there, any kind of signal control bus will carry. Address bus, addresses of the operand, address of the instruction, any kind of address it will carry. Data bus carries the operands. Now let's have a look at the CPU. CPU has a double head. If you observe that the data can flow from the control bus to the CPU, and CPU can further connect with the control bus. There is a two-way arrow, right? This control bus can pass the control bus control signal. Control signal can come from the memory also. Memory overflow is there, right? So that control signal will flow from the control bus to the CPU. Any kind of interrupt is there from the CPU, then the control bus will carry that signal, right? So keep in mind there is a two-way arrow between the CPU and the control bus. CPU, at what address the instruction is there, from where to fetch the operand. CPU has only one-way arrow that the wire goes from the CPU to the address bus, which specifies the location, right? Which specifies the location. That's why there is no address, there is no wire back or no connection back from the address bus to the CPU. Definitely address bus, what it will send to the CPU, nothing, right? So it carries the addresses, or it points to that particular location. So CPU connected with the directional error from CPU to the address bus. Then the data can flow from CPU, because CU is connected from anywhere the data you want to save, or it will be connected via the CU only. So you can perform the ALU also, data will be fetched, then it will go to the ALU. After that, the result is there, then once again it will go to the data bus. That's why two-way arrow is there from the CPU to the data bus. Then comes the memory. Memory, once again, control bus, two-way arrow as with the CPU. IO also, for the control bus, there is a two-way arrow. Control signal can be sent to the devices and can be received from the devices. So address bus points to a particular memory location, definitely an arrow from the address bus to the memory, right? So data bus, once again, two-way. Data can be carried from the memory, or for saving the result, we can go back to the memory also. Then the IO devices, once again, the same I told before also, direct two-way directional arrow from IO to the control bus. Control signal can go to the IO devices. From IO devices also, if malfunction happen or anything happen, a signal will be carried through the control bus only. So there comes the address bus. You can define the location of the any input device or output device also. There is an address bus, two-way arrow is there. So output devices also, data is from the data bus to the output devices. It's bidirectional. So after discussing the CPU connections and all with the wires, there comes the IO system, right? Input output system. So where we will talk about programmed IO. IO system is divided into like three parts: programmed IO, interrupt IO, and direct control buses. As I discussed, also like control signal and all. There is a direct memory access, programmed IO, interrupt, direct memory access. So let's first talk about the programmed IO. In a programmed IO, data transfer between the CPU and IO devices is controlled directly by the CPU using the instructions. I mean, the CPU actually waits until the device is ready, which can waste the time, because the CPU cannot perform any other task during this period. For example, anything is happening. So we want to perform with the IO, CPU has given the instructions to the IO, or IO has given any instruction to the CPU. So that means if CPU, we are asking IO to perform anything, till the time CPU has assigned the task to the IO, and CPU will keep on waiting, whether the task is completed by the any input output device or not, right? So CPU actively waits until the device is ready, which can waste the time of the CPU, and CPU cannot perform any other task during that period, because it's on the continuous waiting loop, right? So programmed IO is where CPU is onto the continuous waiting loop. I mean, once I have assigned the task to you, you are doing your task, I'm waiting until and unless you complete. I cannot and I do not get a signal that you have completed the task, I won't go anywhere, I'll keep on waiting for you, right? So that is programmed IO. Programmed IO has two types. One is known as a standard IO. Standard is also known by with the two other names, isolated and port IO, right? It has the separate instructions to access the IO devices. A set of separate instructions are designed for the IO and separate instruction for the memory, right? IO addresses are different from the memory addresses. IO addresses are different from the memory addresses. That is the isolated IO. IO is isolated from the memory. Then there comes the memory mapped IO, where IO devices are treated like the memory location. So the same instructions we use for the IO and same instructions we use for the memory, right? So keep in mind, the major point to note here is in the programmed IO, we keep on waiting, right? The CPU keeps on waiting for IO to complete its task. Then comes the interrupt-driven IO. Interrupt-driven IO says that, okay, CPU has assigned any task to the IO. IO will carry on with its own operation. CPU will say that, okay, IO, you complete your task, and by that time, I'll perform something else. Once you are done, once IO is done with its task, it will interrupt the CPU and will say that I am done. CPU is not onto the continuous wait. It's known as interrupt-driven IO. So CPU time won't get wasted. It can perform any other task during that time rather than waiting, right? So interrupt it will get from the IO in terms of two things: maskable IO and non-maskable interrupts. Maskable interrupts are like, okay, even if the IO is interrupting me, it can be ignored or disabled by the CPU if needed, right? CPU can mask some interrupts, like if I'm performing some other important task, once the IO will complete, I'll say that I'll mask that even though the IO is complete, do not inform me. I can disable those interrupts and all. Non-maskable interrupts says that those interrupts are like some interrupts are very special and some are the emergency situations. For example, power failure. Automatically power failure has happened. My system will shut down, right? If there is no battery and all. So those are the non-maskable interrupts. Some are the like emergency situations are there. Some interrupts are very priority interrupts are there. So those cannot be masked, right? So then there comes, that is between the IO, interrupt driven IO and programmed IO. Then there comes the direct memory access. So whenever CPU has to perform anything with the memory also, right? So CPU will perform the memory also if CPU is connecting with the memory. As I told that accessing the hard disk, access time for the hard disk is quite high, right? Rather than the primary memory. If CPU will get involved in all these tasks, accessing the memory rather than performing its natural task of processing, and will getting involved in the accessing the memory location and all, definitely we are wasting the time of the CPU. So there comes a DMA controller that is known as a direct memory access controller, which on the behalf of the CPU will perform all the memory operations, fetching the data, like going at that address location and all, it will perform. So there exists a DMA controller which will be performing the task on the behalf of the CPU rather than the CPU getting involved in case of a memory operations and all, right? So then there comes the architecture, RISC versus CISC architecture, instruction set architecture, right? So we spoke about the different instructions in the onto the computer. Von Neumann architecture is there, how they are executed and all. So there is a RISC, reduced instruction set computing, and complex instruction set computing, right? So whenever we are talking about, before discussing all this, let's take a general example: reduced instruction set architecture. For example, can we perform multiply with the addition operation? Yes, right? 2 plus 2 is 4. 2 multiplied by 2 is 4, right? Then 4 multiplied by 2 is 8. Then 2 plus 2 plus 2 plus 2 is 8. Correct? So that means multiply operation can be performed with the addition also. Division operation can be performed with the subtraction and addition also. So why to have different instructions? Why to have different instructions onto the computer if we can perform with the reduced set only? So reduced instruction set computing says that we have smaller set of instructions to perform the operations, right? Complex instruction set computing says that we have lots of instructions to perform every calculation, to perform any operation. We have a different instruction set. So whenever I'm talking about reduced instruction set, that means if the instruction set is reduced, so the format of those instructions, the instruction format would also be like similar and simple. Complex instruction set architecture says that definitely division will take more time, multiply will take more time than addition, so that will have a different instruction set formats, right? So if we have the different type of formats are there. So let's now elaborate on these. CISC emphasizes more on the hardware, RISC emphasizes on the software. So RISC uses more register because one instruction will perform multiple tasks. CISC has less register, but as the number of instructions are more, it will use the more addressing modes as compared to the RISC. So complexity will be high in case of CISC, and in case of RISC, it would be little simpler. So pipelining, as the instruction set format also similar kind. So RISC pipelining would be easy. In case of CISC, it would be difficult. So if we talk about in the computer architecture, the modern trends are there beyond the, like we spoke about the general purpose, general simple computers, block diagram of a simple computer, input, processing and output. And we spoke something about the memory and all. If we come to the today's trend and all, we have multi-core processors are there, in which we are working heavily from last many decades. Also multiple multi-core processors are there, parallel and distributed computing is there. GPUs, different GPUs are there, graphic processing units are there, AI accelerators also we are using from the last few years. And now quantum computing is evolving. So now quantum computing is evolving. So multi-core processor in general, if I say that two or more processing units onto a single chip, right? So we already, like we have 2 core chips are there, 4 core chips are there, we always talk about. So parallel and distributed computing, if I talk about distributed computing located at a different locations and all, the load is balanced, or different locations are involved, the processors are located at the different geographical location, and processing is performed according to the like nearer location and all. So that is parallel and distributed computing. So if we talk about the GPUs and AI accelerators, so graphic processing units, we have a like contain thousands of small cores, definitely thousands of small cores are there, designed for performing many operations in parallel, definitely to enhance the speed and all. They render the graphics, machine learning is there, deep neural network is there. So if we talk about the AI accelerators, so there exist TPUs, NPUs, so hardware optimized data centers which run AI accelerators. So now the future, or I'll say that the currently the work is going on the quantum computing, which uses the quantum bits, qubits, that can represent multiple states simultaneously, right? So it's the, I mean, quantum is the early, is in its early development, and is expected to revolutionize the field, requiring like massive computational power in the future. So yeah, that's all from my end. Definitely I would like to answer your queries also. I think that few questions are there in the chat box now. So why is understanding computer is essential for students who primarily focus on the, okay, it's a very simple question. Like you asked that why the students require to understand the architecture who are focusing on the software development. A simple thing is there, when you define a data type, right? There comes always a data type in any language. You talk about registers, integer, float, where that data is actually getting stored. That is the memory. That is the part of the computer architecture, right? How the components are connected, or how you will solve the problem when there is a common problem when you are doing the programming, is stack overflow, right? A simple program also you write, sometimes it go for the stack overflow. The programming you solve nowadays, or for the placement purposes also, for the software development purposes also, either you solve on the hacker rank or lead code. Have you seen the constraints below? The size of the instruction or the size of the data type, whatever you are giving, it should process the data between 1 less than 1 to 100. So you always use integer, right? 1 to like 2 billion and all. Then you go for the long integer and all, right? Accordingly, you define the data type to optimize your code. To optimize your code, definitely you need to understand the architecture also. And this is very important, even though you are going in the software development field, right? I hope that you understand this. So could you please explain, the next question is, could you please explain how the CPU, memory and input output devices coordinate during the instruction execution cycle? Okay, so once again, fetching the instructions, fetching the instruction, fetching the instruction from the instruction register. No, first the program counter is involved. So what will do, CPU will go to the memory, of course the register address, program counter, memory, it will connect with the memory, it will fetch the data from that program counter register, it will save that. After fetching the data from the program counter, that address, it will go to the memory. That memory, from that memory, it will fetch the data and it will store it onto the instruction register. So this communication will, like, it will connect it. The wires are connected, the buses are connected with all other. As we have seen also, control bus is there, data bus is there, control bus is there, data bus is there, address bus is there. So all these devices, whether CPU, whether memory or IO, all are connected through these three buses. Right? I hope that I answered your question. So next, Paulina asks, what factors determine whether a computer architecture considered efficient or high performance? Definitely, there are the metrics is there, latency is there. So how quickly, or the throughput. Let's talk about a very general metric like throughput. How many instructions a computer process in a defined amount of time, right? How many instructions a computer executes in a defined set of time. So that is how we determine it, right? So yeah, I hope that I answered all the questions. Thank you so much. Right.
Okay, thank you for your presentation, Professor Sugandhi.
Yeah.
And we will go to the next speaker for Miss Cherlina Helena Purnamasari Panjaitan. The time is yours. Thank you. Bu, suaranya belum ada.
Check, check. Okay, thank you. Thank you, Novita, for the time. Good afternoon, everyone. To the esteemed Rector of STEKOM University, Dr. Joseph Teguh Santoso, and to the organizing committee of today's international webinar. Thank you for giving me the opportunity to speak at this webinar. And to the distinguished speakers of today's webinar, let me introduce myself. My name is Cherlina Helena. I am a lecturer in Informatics Engineering at STEKOM University, Indonesia, and I am currently pursuing a doctoral degree in computer science. Well, before I start my presentation, I would say thank you to Professor Sugandhi for the presentation. It was very clear and insightful, and my presentation will probably have some similarities with the material already presented by the professor. So today I will discuss the topic fundamental of computer architecture. First, let me share my presentation. Okay, okay, please wait a minute. I think my presentation. Okay, I will repeat to share my presentation. Okay, I hope the presentation is available in your monitor, right?
Yes, ma'am.
Okay. Okay, I will start the presentation with the same question with Professor Sugandhi. What is computer architecture? Okay, the foundation. Okay, computer architecture is the science and art of designing a computer system to achieve specific functional performance and cost goals. It serves as the fundamental blueprint and contract for computing science. Okay, there is a phrase designing a computer, designing a computer system, and blueprint. The phrase designing of computer system and blueprint comes from the foundational models of how computers are built. Most notably, the von Neumann architecture. This model describes in the 1945 first draft of a report on the IDVAC, or we can say electronic discrete variable automatic computer, is one of the first electronic computers ever designed. And this kind of computer or this machine is very important in the history of computing because its architecture and design become the foundation for almost all modern computer. And the blueprint for almost all modern computer by defining core components such as the CPU, memory, input-output, and bus. Okay, this diagram actually already described by the first speakers, but I want to explain again about this diagram to understand the blueprint about the computer or the computer architecture. We have to understand. We have to go back with this root, which is the model that forms the foundation of almost all the concept modern computer. The component is first is CPU or central processing unit. It is we can say that it is the brain of the computer. Central processing unit or CPU, the function is to execute program instructions and coordinates all system operation. And the structural subcomponent of the CPU is a control unit, the conductor that manages the flow of data and instructions. It is responsible for fetching, decoding, and executing instruction. And then there is ALU or arithmetic logic unit. Arithmetic logic unit is a calculation engine that executes arithmetic and logic operation. And then there is registers, a very high speed memory located inside the CPU for temporary stage, example, program counter, accumulator, and etc. And then there is memory unit or the storage. The function is to store boot data and program instructions. The stored program concept, all of the store is in the memory unit. And then structural characteristic of this is consists of memory cells, each with a unique address, can be volatile or RAM or RAM, or non-volatile or ROM, ROM. Operates operators based on reading and writing. And then interaction between CPU with and memory. The memory unit is the central storage location. It stores all the program instructions and all the necessary data. The CPU maintains a constant two-way connection with the memory unit. The CPU retrieves instruction and data from memory, and the CPU writes the result of its processing back into memory. And then we have the interaction between CPU with input or output device. Input or output device mechanism is like the interface. The function is to act as a bridge between the computer and the external world. The CPU manage all the data that enters the system via input devices and all the results that leave the system via output devices. In essence, the control unit dictates that the arithmetic logic unit should compute using data from registers and the memory unit, and coordinates communication with the external world through input-output devices. Input device is such as monitor, keyboard or mouse, sensors, something bring information into the system, and the output device such as monitor, printer, actuators, something that output the processing result. Input-output controllers specialized circuits that manage communication between input-output device and the system bus. Okay, this is the explanation about the diagram before that I have explained. Okay, and then we have diagram. Okay, diagram. Von Neumann model, the basic blueprint. This diagram is a communication or bus system of the von Neumann architecture. So we have three system bus here. System bus and we can see system bus as like similar with interconnection system. Yeah, system bus is same with interconnection system, and some people say interconnection system or system bus is the highway. The system is essential, the communication backbone of the entire computer. Its main function to provide the means to link the CPU and then memory unit and all input-output devices together, facilitating the transfer of data, memory address, and control signal. The system bus itself is structured into three distinct parts. The first is data bus. Data bus is the highway for actual data transfer or bidirectional, and then address bus carries the address of the target memory or input-output device, or we can say unidirectional from the CPU. And then control bus carries control and timing signal to coordinate operation. For example, read or write signal. Okay, this is the explanation that I'm already explained to you guys. And then we have this diagram. This diagram is fetch, decode, execute cycle of the von Neumann architecture. This diagram is share an iterative process executes by the CPU billion of times per second. This component interact dynamically through the computer's heart cycle. So the computer heart cycle we can wrap up with three things maybe, or the cycle is fetch, decode, and execute. It follows a continuous loop called the instruction cycle, which has the four step. Actually, the four step: fetch, decode, execute, and update. Fetch is the start of the cycle. The cycle start with fetch. Think of this as the CPU finding the next command. The program counter tells the CPU address. The program counter tells the CPU the address of the next instruction. This address travel along the address bus. The CPU then uses the data bus to retrieve, or we can see fetch, that instruction from the memory and bring it back inside. And then next step is decode. Decode, once the instruction is inside the CPU, the control unit take overs and it interprets the instruction, figuring out what task needs to be done. Is it addition? Is it a data move? The control unit essentially translates the code into the command. And then execute. This is where the work happens. If the task is a calculation, if a task is a calculation, the ALU or arithmetic logic unit perform the necessary operation. If the instruction requires data, say fetching a number for the calculation or saving a result, the CPU will use the buses again to get or store. The CPU will use the buses again to get or store that data from the memory or an input-output device. And then update. After executing the instruction, the CPU must prepare for the next step. It simply updates the data counter so that it now points to the location of the next instruction in the program, and then the entire cycle starts all over again. So this is the cycle that continuous loop in the computer. Okay, this is the explanation that I have told you before about data flow in the von Neumann model, the fetch, decode, execute, and update cycle. Okay, and then, however, this model has a fundamental limitation that has spurred innovation for decades. So, the von Neumann bottleneck is a is a main limitation of this model. The problem is the processing speed of the CPU is limited by the data transfer bandwidth between the CPU and memory via the system bus. And then architecture solution is the development of memory cache, memory cache, integrated memory controllers, and multi-core architecture aim to mitigate this bottleneck. Okay, we have three key perspectives about the computer architecture. This is the programmer's view or the contract, and then the designer's view or the structure. This involves the high-level design of the major functional component and how they interconnect, and it is based on foundational models like the von Neumann architecture, which outlines the core part, the CPU, memory, and input-output system, all connected via a system bus. And then the engineer's view, or the implementation and trade-off. This is also called microarchitecture. It refers to how an ISA is implemented for a specific processor. So the next we will talk about the ISA. And before it, this is the attributes included in the architecture, such as instruction set architecture, memory model, interrupt handling mechanism, and addressing modes. Okay, so this is the core relationship what versus how. Instruction set architecture or ISA is the what. It defines the contract between the software and the hardware. It specify what the processor can do, what instruction is understand, and how a programmer can use them. And then microarchitecture is the how. It defines the implementation of that contract. It describes the specific design techniques and engineering choices used to build a processor that executed that ISA. Okay, maybe because the time I will explain quickly. So sorry about this error. Okay, what is the ISA or the public persona of the processor? Think of the ISA as the public persona of a processor. It's what the software, the operating system, compilers, and applications sees and interact with. It defines the set of primitive combination, uh, the exposed to the programmer, like the software rights, and then the hardware rights. Okay, there are some key components of an ISA. First is instruction set, the vocabulary of command. This includes arithmetic instruction, data transfer instruction, control flow instructions, and logical instruction. And then register file, the definition of the small, fast memory location directly inside the CPU. Like how many registers are there, what is their size, what are their specific purpose is all in the register files. And then memory addressing modes, or the grammar for how an instruction specifies the location of its data, like immediate, register, direct, and indirect. And then that data types, the fundamental types of data the hardware can natively recognize and operates on. For example, bit bytes, bit integer, bit floating, point numbers, and etc. And then memory model defines how memory is organized and accessed from a program's perspective. A key concept here is whether the architecture is byte addressable. Each byte has a unique address which is common in modern systems. And then the last key is input-output model specifies now the CPU communication with peripheral devices. Okay, why is the ISA so important? First, software compatibility and portability, and then separation of concern and innovation. Software developers can write code without needing to know the intricate details of the underlying hardware's pipeline depth of change size. And then hardware engineers can continually innovate and create new, faster, and more power-efficient microarchitecture without breaking existing software. As long as the new chip honors the ISA contract, all old software will run off it. And then the ASE pros as a stable contract enables the entire modern computing ecosystem have defining computer families. Okay, so we talk about after understanding and after we talk about the what, now we explore the how or the hidden implementation called microarchitecture or the engineer's view. The microarchitecture is the hidden implementation that execute the ISA. It is transparent to the programmers. I break it with three column by category, description, and implementation choices. The category of pipeline design is how the instruction execution is broken into smaller sequential stages. And the implementation choice is 5 steps versus 14 stage pipeline or handling of pipeline hazards like data control or structural. And then the next category is superscalar and out of order execution is the ability to execute multiple instructions per cycle and reorder them for efficiency. And then execution unit and parallelism is a capability for parallel instruction execution. This is the implementation choices. And then branch prediction is the mechanism for guessing the outcome of conditional branches to keep the pipeline full. Implementation choices like algorithm complexity, size of the branch history table, and then cache hierarchy is the design of the fast memory subsystem between the CPU and main RAM. And then memory controller is how the CPU communicates with the main memory or RAM. And then power management is the technique to reduce power consumption and heat. Okay, that's all my presentation. I'm so sorry if maybe my explanation is not clear for you. I hope my presentation quite give you some insight or some new knowledge. And I'm so sorry because I have to continue my schedule to teach. So maybe can I just answer one question, Miss Novita?
Yes, it's okay, ma'am.
Okay. Okay, maybe I just answer one question from Farid.
Yes, please.
Okay, may I ask how modern architecture such as multi-core processors improve performance compared to traditional single-core design? Okay, modern multi-core processors improve performance over traditional single-core design through parallelism, higher throughput, and greater energy efficiency. Uh, why single core scaling stopped working? Before multi-core chips become popular, CPUs improve performance by increasing clock speed or uh, GHZ, GHZ and increasing pipeline depth, optimizing instruction execution like superscalar, out of order, branch prediction. So a single core cannot be made much faster without burning too much power or wasting cycle waiting for memory. Because this hit limits power wall, instruction level parallelism limits, and memory wall. So how multi-core improves performance? Instead of trying to make one core extremely fast, CPUs now use many efficient cores that run tasks concurrently. So um, we need parallelism, higher throughput, and greater energy efficiency to improve performance over traditional single core design. Okay, maybe that's all my answer. I'm sorry for the uh, mistaken that maybe I share to you. I hope the next speakers can perfecting my presentation. Thank you. I give the time back to Novita.
Again, thank you so much for your presentation, Ms. Cherlina. And we will go to the second speaker, Dr. Sivakami, as Assistant Professor, Department of Information Technology. The time is yours. Thank you.
Hello everyone. First of all, I thank the organizers of STEKOM University for giving me the opportunity. I introduce myself. I am Dr. M. Sivakami, Assistant Professor, Department of Information Technology, Dr. Umayal College for Women, India. I welcome you all for the third session of international webinar. Today's topic is Fundamentals of Computer Architecture. As we all know that computers do not grow powerful by chance. Architecture only makes them powerful by design. Today we explore the fundamentals of architecture of power devices, data, digital transformations around the world. Screen. Is it visible now? In the past two sessions, we saw both what is computer architecture. So computer architecture is nothing but the design and organization of computer core components, how they work individually and together to execute programs efficiently. It defines the structure, behavior, and the interaction of various hardware components. We all know that computers are classified under the based on size and capability. There are microcomputers, mini computers, mainframe computers, supercomputers are all we know that. Now we are talking about server computer, embedded computer. It's a embedded computer is nothing but a part of another device connector in cars, engine, microwave, and all. Workstation computers is a study about the complex problems to run laptop, and analog computers are used a real-time life task, that is measuring temperature and all, whereas a hybrid computer is used as wearable devices used in patient monitoring systems. So, we know that the components of computer systems are input unit and control unit and output unit. Through the mouse, keyboard, and microphone, we fed the information to the system, and the control unit consists of arithmetic logic unit, memory, and additional is a main memory and secondary storage are there. After that, the processed information is going to monitor through output unit. The dark red coated line denotes the data path, and the dotted lines denote the control path here. Here, the memory depicted in this slide is bridges the gap between input and output and the processor control unit. So it plays a vital role here. The types of memory here is primary memory and secondary memory. So we focus on memory about this in the upcoming slides. So motherboard here is used to transfer data between processor, memory, and storage devices. So without this, the information cannot be passed to various components of the computer. So the bus structures is depicted. The system bus is consists of data bus, address bus, and all. So it passes through the various components, input, output, memory, and processor. So it is used for transfer the data between the components. So types of bus here, the data bus, address bus, and control bus. Data bus, as the name itself depicts that it transfers the data between the different components of the computer. Address bus is nothing but used to communicate the address of a particular component which is used to communicate with other devices. The control bus is used to transmit different commands from one component to another component. So as the memory is a topic, I'm going to continue. The data storage, we have to know about the data storage. Bit, it's nothing but a single binary digit, either 1 or 0. Byte is a combination of 8 bits, and a kilobyte is 1024 bytes, and that is megabyte MB and gigabyte GB, terabyte TB, and petabyte PB. All the used for data storage. Next, about the memory, the two concepts going to discuss the purpose of what is the purpose of memory. Memory is used for the purpose of running our programs. Without the data, the program cannot be concluded. So we have to store the data in particular storage that is called memory. So it is satisfy the input and output interfaces. So performance, how to achieve measure the performance of memory based on the concept memory latency, memory bandwidth. So what is called memory latency? It is a time to require. It is time to require to obtain a certain data. It is in the process of access time and cycle time. What is called access time? The time is between the requested word and the word what is it's arrived. It is called access time. What is called cycle time? It is the minimum time interval between two operations that is called read and write operations. Between one read and write operations, what is the time is happening is called cycle time. The next one is memory bandwidth. So without the bandwidth, the data cannot be accessed. So how it can be fasten the bandwidth, the process will be faster. So there are various levels of memory are there. We have to know about that. Level 1 is nothing but a register. Register is a data stored immediately in the CPU. It is resided in the CPU itself. It's a faster access to store the data. Usually accumulator is the repeated one register. Basically accumulator is the register. Level 2 is cache memory. It is a fastest memory that has faster access time. It is located separately. The level 3 is main memory. It is a memory on which the computer works currently. It is a small in size. Once the power is off, the data no longer stays. So level 4 is secondary memory. It is an external memory that is not fast as a main memory, but stays permanently. The data will be stored even after the power is off. The same is depicted in the picture. The types of memory. Memory is broadly classified as primary memory and secondary memory. Under primary memory, ROM and RAM is there. ROM is classified further into PROM, programmable read-only memory, erasable programmable read-only memory, and electrically erasable programmable read-only memory. The RAM is further classified as static RAM, dynamic RAM. The secondary memory is classified as disk drives and tape drives. Tape drive is nothing but magnetic tapes, and whereas disk drive is floppy disk, hard disk, optical disk. USB flash drives also. Here the optical disk is further classified into compact disk, read write, and DVD, digital versatile disk, and the sample pictures are here are for RAM and a USB and a floppy disk are depicted here. So the types of memory previously we discussed here is the programmable read-only memory. The content cannot be erased. Once a return means the content cannot be erased. Whereas in erasable programmable read-only memory, we erase the content of ROM by exposing it to ultraviolet rays. And electrically erasable programmable read-only memory, in this we can delete and we can reprogram it. So there is options in it. When we are considering about magnetic tapes and all, it is just a plastic film with a thin magnetic coating on it, used for recording the data. Magnetic disk is a circular metal which are in magnetized surfaces. Optical disk is a laser-based storage. So when it comes to understanding the memory system, how it is resided. So here we are seeing the primary storage, secondary storage, and offline storage. In the primary storage, there is a CPU, central processing unit. In that, arithmetic logic unit, ALU, registers, and cache memory there. So as we already discussed that a memory bus bridges a gap between the processor and the main memory. So here is a resided in between the two memory bus, and the one is main memory, and the second one is secondary storage, and again is offline storage. So the cache memory only the opportunity to communicate with both the secondary storage, offline storage. As it is resided in the primary storage, it can communicate with the main memory also. So it plays a vital role in the architecture of computer. So the next slide, we are saying about the registers. So registers nothing but a small storage unit. It is resided in processor itself. So if you want to store or access any data, means it is very fast because it resided in the processor. So here some MAR means memory address register, MDR means memory data register, program counter, instruction register, and small unit of registers are there starting from R0 to Rn. How many registers we want to accumulate, we can add it according to the problems. So arithmetic logic unit is here, control unit is there. The same is described. Accumulator, it is the most frequently used register, usually used accumulator only. The next one is MAR, memory address register. It, as the name depicts that it holds the address of the location to be where to be accessed from the memory. Memory data register, the name that data to be written into the or memory written into the memory or read from the memory or particular locations. And there are so many registers were noted that R0, R1, R2. It's a general purpose registers. It's needed during the ongoing operations. Program counter is used to keep the track of the program execution. Instruction register, it holds the instruction is just about to be executed next. So stack pointer points to the top of the stack, which is a part of the memory to store function calls and other operations. Flag register is a variety of flag registers are there. Zero flag, carry flag, sign flag, and over flag, parity flag. It contains whether 0 or 1. 1 means it is present, 0 means it is absent, according to the problems. So what is the purpose of registers? Registers play an important role used by CPU. It's storing it. What it stores, it's storing nothing but an instructions. Holding answers while using mathematical calculations. There are some temporary data to be stored of that. So we need the registers. Quick access, registers like computer quick access, so it can grab them fast and we can store and retrieve the answers very fast. So our slides will be focused on cache memory in the upcoming. So cache memory, what is a cache memory with how it is communicated with main memory. So cache memory resided between the processor and the main memory. What is the purpose of a cache memory? It is a purpose to bridge the performance gap between the fast performance of CPU and the slow performance of main memory. So speed up the overall system performance by reducing the time it takes for the processor to access data. So it plays an important role between the processor and the main memory. So working method of cache memory. When the CPU needs data, it first checks the cache memory. The data is found in the cache memory, it is retrieved very quickly. If the data is not there, its CPU fetches it from the slower main memory. The data is then copied into the cache memory, replace other based on specific policies. Previous data will be deleted and the new data only be copied in the cache memory. So it will be available quickly for further request. So here the first one is a central processing unit processor. The middle one is cache memory and the last one is main memory. So the processing start is fast and slow is mentioned here. The word can also be transferred. The block can also be transferred between the memories. What are the advantages of cache memory? It is faster when comparing with the main memory. It takes less time while accessing the data from the memory. It stores the temporary data for the temporary use. Disadvantages of cache memory: since semiconductors are used, it is very expensive. The size of the cache is also usually smaller. We cannot store much of the data in the cache memory. So what is the difference? Both are storing the information, cache and registers. What are the major differences between cache and registers? Cache, store recently used data. Registers, what the data is the processor currently processing. So that data is stored in the registers. When compared the cache is smaller, faster memory unit. Registers is smallest memory unit. Cache is resided in a separate location, but registers are resided in the CPU itself. So the accessing can be easy. In cache, the access times are longer because it has to communicate with the main memory. If it does not respond, it will have to wait and get the data. So registers means access time is shorter when comparing with the cache. Cache is more expensive because the semiconductors are used here. Registers less expensive while comparing with the cache. So role of a cache memory during browsing. Cache memory usually stores images, scripts, styles during the website browsing. So it is a repeated visit. So to load pages faster on repeated visit. Reduce internet data usages. We not need to browse again and again because it already saved in the cache memory. We can use it. So reduce the internet data usage by avoiding repeated downloads. Improves user experience because of speeding up the page load times because it is already stored there. So it will speed up the process. Helps offline viewing. It's, even if we are downloaded means in the offline storage, we can previously visited the pages, so we can view it. Lowers server load because of fewer requests are sent to the website server. So much more are downloaded previously in the cache memory, we can view it so that fewer requests are sent to the server. So it lowers the server load also. How the deletion process of cache memory is handled. When storage is full, when we are talking about the issues of storage, it will delete the recently used LRU, recently used concept from the cache memory. So storage will be full. To free up space, when it grows too large, it consumes too much of storage. So we have to delete the cache memory and the content of cache memory. When data is outdated, so previously downloaded data is not needed further. So cache can hold old versions of files and all can be deleted to store the fresh copies again. So for security reasons, clearing the cache can remove stored personal information like password, cookies informations, images, profile informations and all. So for security reasons also, we can clear the cache updated. The troubleshooting step. Deleting the cache is a common first step for troubleshooting because a website or application is not working correctly. We have to delete the cache and then enhance the process and start the process again. So for a troubleshooting step also, we have to delete the cache memory. So it's a real-time instance that we are facing while not clearing the cache memory. In United States, in the year of 2017, they faced Cloudflare incident. That is, the cookies, passwords, session tokens, or leaked into cached pages. So the attackers use that same information to stolen the previous persons. So it affects millions of websites globally. So the Google Project Zero is discovered the leakage and it is cleared the cache. So the next problems in United States in the year of 2019, content delivery network. It is connected to Facebook. So the wrong informations or connected the user's profile information to some other persons. So the wrong communications is connected. So it is also led to some mistakes. So we have to clear the cache memory at the date. So next one is United Kingdom. In United Kingdom, in the year of 2021, there is a problem called NHS COVID app 19 app is there. In that, medical persons observed that wrong exposure notifications are shown, that high risk contact alerts are there, and more number of persons are affected now itself because it's not a correct information. The previously downloaded information shows that high risk contact alerts are there. So it is a wrong information to the medical persons. So they avoided the NHS COVID-19 app there because of the cache error. The next we are going to see that fourth issue is in Japan 2018 Rakuten website cache poisoning attack. So when you are browsing on a website, it leads to some phishing sites. It's not a correct sites. It is led to phishing sites because of the previously information stored in the cache. It led to some unwanted sites while browsing the websites. So it is also problems that are raised in the time of 2018 in Japan. So next one is Germany in 2022 Dashed Park website cache issue. In that, passengers are seeing the old or invalid train schedules only because cache corruption occurred after backend system upgrade. So this led to affect thousands of trip planning queries for several hours. So we have to delete the cache memory up to date. So this led to the problem. So in necessity of to clear cache, if cache memory occupies a large, cache grows over time, it occupies significant storage space, so we have to clear it. Old cached files conflict with the updated website content. It may load incorrect information, for example, in banking, email, or exam portals. It increases attack also. So browsers may slow down due to excessive data. So privacy risk. Cache may store sensitive thumbnails, forms, or browsing traces. So fixes website errors like page not loading, stuck screen, CS not updating, etc. So we are concluding that emerging memory technologies are here. These technologies aim to combine the speed of RAM, excuse me, These technologies aim to combine the speed of RAM. So while we are trying to increase the speed of RAM and the storage of a RAM, the emerging memory technologies will be followed, that phase change memory, PCM. It is in the electrical resistance of a material. It contains electrical resistance material to store the data. The next one is resistive random access memory, or RAM. It's suitable for embedded systems and AI applications. The next one is magnetoresistive random access memory. It is nothing but embedded memory, which is available in microcontrollers and high performance computing cache and all. So it is a magnetoresistive random access memory. It is used in microcontrollers. And the last one is ferroelectric RAM, FERAM, very low power consumption, faster in writing the information. These are all the emerging memory technologies now arrived. Thank you. Thank you for the opportunity given by STEKOM University and our head of the institution by Dr. M. Sivakami.
Okay, thank you so much for your presentation, Dr. Sivakami. And we have 3 questions from participant. For first question from Mr. Afif, could you elaborate on the main difference between the von Neumann architecture and the Harvard architecture, and when it is typically used? Thank you. The question already read in the Zoom chat.
Actually, design problems, three goals often conflict. One, why is the key design challenges is performance per watt, higher clock frequency increases, power, heat, thermal limit. Hence, based on requirement, we need to design. Thank you.
Okay, thank you. And then the second question. Oh yeah, okay. We will go to the next speaker for Mr. Letus Senzani. The time is yours. Thank you. Yeah, for Mr. Lexus, you can start this special presentation. Thank you.
Hello, thank you very much. I hope I can be heard.
Yeah, sure.
Can I go ahead? Can I go ahead? Oh, wow.
Yes, please.
I seem to have a bit of network problems, but we'll make do with what we are able at the moment. I've missed most of the first presenter's presentation, so some of my presentation may be a repeat of what has already come through. But I really want to consider the history of computer architecture. Basically, the world, well, man has always been trying to keep records and also process data to get information that will help make decisions. And in the olden days, this was a little difficult because they relied on manual methods until we come into the mid 20th century, when discoveries in the field of electrics and electronics led into building machines that could more or less like think. And the first ones, just a brief history, were really based on the vacuum tubes. And why vacuum tubes? Well, because to use electricity to do any processing at all to represent, data, the best was to really rely on just the two states that electricity allows you. That's being on or off. Now, this then was what vacuum tubes were able to do, because they could give you a charge when the vacuum tube is on, representing a piece of data, and off means another state of data. Now, this fitted the binary numbering system. Now, in the binary numbering system, because you are only looking at the state of being on and being off, it resulted in you being able to represent any numbers in the binary system by using the vacuum tubes. Now, further developments came to a smaller component, the transistor. So now it was possible to keep a charge or not keep a charge and represent a 0 or a 1. And developments in the transistor then ended up making the transistor even smaller, so that in a surface area you could fit more transistors, and so you could put in more zeros and ones. You could put in more on-off features. Basically, what I'm trying to say here is the transistor was formed into a combination of transistors that either kept a charge or did not keep a charge. And that represented a 0 or a 1. Now, a combination of this type is called a flip-flop. With the flip-flops, you can combine several of them to have a combination of zeros and ones. And so we are able to represent various pieces of data using this combination of zeros and ones. Today, we are actually using transistors that are really quite small. They are microscopic even, so that you can fit in a surface area a lot of them. And this allows a higher processing power in the computer, because bigger and bigger numbers can now be represented. So this brings us now to how this combination is now able to do any processing at all. In the history of mathematics, a gentleman called George Boole came up with logic algorithms that would result in either logically two states, either being on for true or off for false. Now, the result of this then allowed algorithms that would bring out binary numbers at the end. And this is what has been incorporated in the processor of a computer. I'm trying to really compress a lot within the time allotted. You'll bear with me. Now, with this combination, then you could build a processor containing many flip-flops and carrying representations of various data. And now, using the Boolean algebra, data could be manipulated to arrive at information also represented in flip-flops, but able to be seen using methods that were used to translate, that are used to translate to what the human being now can see. Now, we have gone from using only 4 of these flip-flops to now using 64 of these flip-flops within the processor of a computer, and a combination of several 64 processors, 64 flip-flops is what gives us the 64-bit machine. Now, in binary numbers, if you have 64 places to actually represent a number, you will represent a really large number. Now, the way the processor works is it will address each of these flip-flops using an address area, which itself is made up of flip-flops that are specialized for pointing to the various areas in the processor, the various areas of memory in the processor. Now, that has now brought us to the level where we have machines that can think better, that can think faster, that can process more complex data than before. And this is why we have been able to come up with the very small gadgets like cell phones, which are basically little computers per se. Now, the way then that we are able to see the data is by combinations of software that interprets the zeros and ones to what the human can now understand as characters and numbers. Now, for the representation of characters as binary numbers, the world came up with a table that translates numbers to characters and symbols called the American Standard Code of Information Interchange, shortened to ASCII codes. So a capital A will have a binary combination that represents a capital A. A small letter A will have a combination of binary numbers that represents a small letter A. But at the same time, you are able to differentiate, the computer is able to differentiate between in the binary number representations, that these are representing characters and symbols, these are representing actual numbers. And that's how then this is using that software translated to what we actually see on the screen. Computers have developed quite a lot since the first ones came out in the 1940s. I would say it is an elaborate job to really understand what goes on behind the computer. The beauty of it is the brains that be have brought us to the level we are at now. I would want to go this far with my presentation. Thank you very much. Am I being heard? Oh. Am I being heard?
Yeah. Yeah, sure.
Yes, I am done with what I was unable to actually to put the PowerPoint up. I think I'm having network problems this side.
Yeah, it's okay, Chair.
Sure. And I don't know, do we get the questions now?
Yeah, we have some question from participant. For first question, what foundational knowledge should students gain if they want to pursue deeper study in computer architecture or hardware design? The question already read in the Zoom chat also.
I didn't pick that one up, sorry.
Okay. What are the biggest design challenge engineer face when trying to balance speed, power consumption, and hardware costs?
I think I'm having problem with the accent.
Okay.
I don't know, is it possible to just put it on text and
Yeah, it's okay,
put,
sure.
yeah,
Already read in the Zoom chat.
okay, all right.
Yeah. We're still waiting. You can write the answer in the Zoom chat also. Okay, and before I close this event, for all participants, please open your camera. I will take a picture on the count of three for documentation. Okay, one.
Okay, so I should
Yeah,
switch on
partner.
the camera?
Yeah,
Okay.
it's okay, it's okay. Yeah. Okay,
Okay.
1, 2, 3. Again, another one. 1, 2, 3. Yeah, thank you for your cooperation. Finally, we come to the end of webinar today. We would like to thank you for our speaker for the wonderful information and sharing your knowledge. We hope this information will be beneficial for our participants. At least we hope to have more collaboration in the future. The webinar for today and here. We hope to see you soon. Thank you and have a nice day and goodbye.